As I said tonight, I kind of just want to share my personal experiences with 3D printers, which are not all incredibly positive, but I have had some good times with 3D printers. I hope that this talk can be kind of an in-between between very pessimistic and very optimistic. However, personally, I believe the media has been entirely a little too optimistic, and it's my goal to maybe shed some light on the limitations and realism around 3D printers, but we'll see how we do. So basically, I'm going to talk a little bit about myself, the Invention Studio, which is a really neat place that I'm really involved with. My experience with 3D printers, how I think they're terrible, some common misconceptions about 3D printers, things that they're actually good at, and then where I think 3D printing is heading in the future, possibly a future where we're not all around because 3D printers have killed us all off and become sentient and started their own society. Then we'll have some time for Q&A, hopefully. But again, feel free to ask questions during the talk. So I'm Chad. I like building things. Sometimes that involves nuclear reactors, sometimes that involves 3D printed things, sometimes that involves race cars. I like to have a good time. And I'm a senior in computer science at the Georgia Institute of Technology, and currently the president of the Georgia Tech Invention Studio. Again, we'll sort of talk about that in just a second. And in what little free time I have, I also do some research and eat a bunch of ramen. So yeah. And this is basically a short overview video about the Invention Studio that does a really good job of showing what we're all about. In a general sense, we are a by-student, for-student machine shop / hackerspace at Georgia Tech, which is really nice because we get Georgia Tech money to do normal hackerspace things. So we have lots of really awesome machines and many, many 3D printers. So that's where I've gotten a lot of my experience from. But to give you a general idea of who we are and what we're all about, I'm just going to go ahead and show you guys this.
The Invention Studio is this magical place where they have basically every tool that you could possibly want to build something, and most of them are tools that no person could ever possibly afford.
What we're doing here is actually completely new, not just at Georgia Tech, but everywhere.
We're all teaching ourselves and teaching each other and creating a sort of collaborative environment where knowledge flows really easily.
It's kind of helping reshape and kind of mold the future of education. Really, much more of this kind of maker, creator, hacker culture.
We went from having 10 students in one room to having 5 rooms, and we're up to like 60 students right now running the shop.
We keep the doors open, we keep the machines running.
We're sure that all of the safety protocol are met.
On a monthly basis, we have around 500 different people coming in from across 9 or so different majors.
When you really get mechanical engineers and you get industrial designers and you get material science majors and you get biomedical engineers, and all these majors literally coming together and sitting down at a table, you get completely different ideas.
There are some really cool people here doing some really crazy things.
I was cutting out the lid and base for a Faraday cage for our particulate accelerator.
I'm working on improving my BattleBot. We've been playing around with making some jet turbine wheels.
I'm working on my steel string acoustic guitar. I'm working on an experimental model aircraft.
I'm working on a 50-kilogram satellite.
In order to keep the Invention Studio open and available to all students, it takes lots and lots of funding. That money comes from our generous corporate sponsors, as well as the tech fee that we get annually. The great need is to have a building, an entire building dedicated to the idea of interdisciplinary design and bringing the maker movement back into engineering and engineering schools.
So this was made about a year ago. Since we've gotten another room, we have about 80 student volunteers now and about 1,500 students and researchers that come through on a monthly basis. And again, it's all entirely student run. which is really neat because you get to come into the Invention Studio and work on something with another student helping you out, not necessarily some machinist who's been around for forever and is going to look over your shoulder the entire time and tell you everything that you're doing wrong. We're sort of just there to yell at you and tell you to use clamps, or that, hey, don't do that or you're going to cut your finger off, you know, basic things, and then everything else is up to you as a student. You basically have free reign over whatever you want to use. Sorry, I can't figure out how to get this to go back full screen, so we'll just do this. But the other thing that goes along with us being student-run is that we have students fix and maintain all of our machines. And I took responsibility last year of maintaining all of our 3D printers, which basically resulted in me spending about 40 hours a week in our back room, which is this like basement room with no windows, so no natural sunlight. It's like the 3D printer cave, just surrounded by broken 3D printers every day, and you know, having to work on them all the time. So a lot of my views expressed in this presentation are kind of a result of that year of living among the 3D printers and working on them every day. But basically, we have 3D printers in the studio because we think they are cool, developing technology, emphasis on developing technology. They've certainly come a really long way in like the past 5 years or so, and I think they still have a really long way to go. Progression is fairly quick in the industry though, because it is fairly big right now, but we like to have 3D printers as a rapid prototyping technology, and I think that, again, emphasis should be placed on those words. These are kind of the takeaways of the entire presentation as far as what I think people should understand about 3D printers is they are a rapid prototyping technology, very good for prototyping things, not necessarily as much for finished products, and we can talk about that in a little bit more detail throughout the presentation. Sometimes they're acceptable for short-run manufacturing, like for instance if you're doing a plastic case for your Raspberry Pi or something like that, you have a custom Raspberry Pi router or something like that you're only making 10 of for your prototype for a Kickstarter. That's acceptable as well, and they're decent at that. They are good for bespoke parts as well, and there are a lot of companies on the internet now that are kind of popular that'll make you custom bracelets and things like that, custom watches, and that's a pretty neat thing that 3D printing has brought to the marketplace that not many other fab shops are able to do in an economic fashion. And since they're additive manufacturing, you get to save a lot of material. And we also draw in a lot of non-engineering students into a machine shop. And you know, once they get tired of 3D printing, we can say, oh, so now that you're in the machine shop, even though you're a liberal arts major, you should also learn how to use our CNC mills and water jet and laser cutters. And we get to turn this literature major who was initially interested in 3D printing into a badass machinist at the end of the day, which is really cool. And it's certainly awesome to see a bunch of electrical engineers and biomedical engineering students or liberal arts people come out of Georgia Tech with not only a degree in whatever their field is, but also a bunch of machining experience, which allows them to go into the industry and have some manufacturing knowledge as well. As far as common materials, we deal mostly with FDM style 3D printing, which I should probably talk about first. So there are several different flavors of 3D printing. FDM is called fused deposition modeling, and I had the chance to meet the guy who initially made the patent for FDM and asked him, you know, how did you come up with this idea? And he said, well, my daughter had this plastic frog toy that broke one night and I just wanted to make another one in-house, so I grabbed a hot glue gun and I just made layers in the corresponding shape of the frog until I had a bunch of layers piled up that resembled the frog, and realized I could take this hot glue gun and strap it to a plotter and then put a Z-axis on the plotter so it could move up and down, and then he had his first FDM style printer. Now he owns Stratasys Corporation, which is probably one of the largest industrial grade 3D printing companies in the world, which is pretty neat. But FDM also happens to be sort of the cheapest consumer grade printers. They usually use, like on this slide, it says ABS or polylactic acid, PLA, which are two thermoplastics that are fairly common in industry. For instance, ABS is the plastic that Lego are made out of. So it's everywhere, it's pretty easy to work with. They have different sort of structural qualities. For instance, ABS tends to shrink as it cools down. PLA is a little easier to deal with. You don't have to have a heated build platform. But we've kind of played around with all of these different materials here. We have some neat filaments now that are actually like wood pulp composite that's put together with an epoxy that you can melt and then have like a 3D printed wooden part, which is pretty neat. Or Ninja Flex. We've actually had a couple of students come into the Invention Studio and print shoes out of Ninja Flex, which end up not lasting very long, but it's cool to see a part that was made before you in real time that you can put on your foot and walk across campus in. So that's pretty neat. There are also stereolithography, or SLA, and selective laser sintering, SLS or SLM for selective laser melting. And these SLA and SLS machines are usually much more expensive. We have a couple of them. For instance, we just got a Form 1 printer, which is SLS, and basically has a photopolymer resin that has a light on the bottom, and you essentially shine a light onto the photopolymer resin, and where the light hits, the photopolymer resin hardens. And what that allows you to do is make a much more detailed part than FDM would typically do. So like I said, FDM is basically like taking a hot glue gun and laying down in layers until you have an entire part. The interesting disadvantage with this, though, is what we say is anisotropic structural qualities of your part, meaning that with laying down a part layer by layer, sometimes you don't necessarily have a uniform fusion from layer to layer. So what that means in essence is that most 3D printed parts are not very structurally sound. So you wouldn't want to make like a steering linkage or something that your life is going to depend on, or a lot of mass is going to impact itself on from 3D printing, because you'll have areas of the part that are better bonded than others. And sometimes that results in a part that's really strong in one area and not so strong in another area. So there are many design considerations that must be sort of taken into account when you're 3D printing, and that's just one of them that's particularly limited or limiting in FDM style manufacturing. So just to give you a rundown of our fleet and what printers I've had an experience with, we have a whole lot. 2 Voltspots AO101s, we have 3 Replicator 2s, one of which I've got in the other room. It did a particularly great job of demonstrating my point of why 3D printers are aggravating last night. A group of like 6 of us stood around the printer for about an hour trying to get it to 3D print and just continually watched it fail epically. We also have a bunch of up minis, which are really nice. If you look at the up minis and then you compare them to like a Stratasys Dimension, they're all nice and closed off. This is like something you could see in your, sitting beside your computer, kind of looking at home next to your PC tower. It's nice because it's all in one box and it's closed off, which means that the entire build volume is heated. Like I mentioned earlier, ABS actually shrinks somewhere between 3 and 6% as it cools down. So you kind of have to close the entire area off, and if you don't, you're subject to air currents which can flow through the build volume while you're printing and shrink certain parts of the print before other parts of the print, and you end up with malformed parts, which is kind of hilarious sometimes. The Voltsbot TAZs are also ABS printers with heated build platforms, but they do not have an enclosure, so they're often subject to lots of problems. We also have a bunch of H-Series and Up Plus 2s, which are like the older brothers of the Up Minis. Now we have all of these in heated enclosures, which is really nice. Have a couple of Type A Series 1s, which are absolutely huge. They print PLA. And here, just to give you an appreciation for how quickly things change in the Invention Studio, we had a modified version of this talk at DragonCon this year, and when that talk was giving, our Replicator 2s were alive, our Series 1s printers were alive, our TAZs were alive, and our AO101s were alive. They've all been put out of their misery now, and sort of taken away for other projects and taken apart and transformed into more useful things. But at the same time, we are starting to grow really rapidly in the number of 3D printers we have. We have about 30 now, all in one big room, so you can walk in and do whatever you want on them. But that sort of includes mostly FDM printers, so the Up Minis, the Affinias, the Replicator Z18s, and the Dimensions are all FDMs, and then the Formlab Form 1 and the Objet are SLS printers, which do really high resolution stuff out of photopolymer resin. So as far as why 3D printers are terrible, this is one of my favorite YouTube videos, and this kind of encapsulates just about everything that's frustrating with 3D printers. So what is happening here, this printer is supposed to be printing a Raspberry Pi case, which is basically some simple rectangles, and has instead decided to make this ball of just wasted hopes and dreams and PLA filament. And I was talking to Alan Fay earlier from Freeside Atlanta. They're kind of down the street from Georgia Tech, and they have a couple of 3D printers as well. And really, the thing with 3D printers is you have so many variables to take into account for the operation of this machine. So you have all of the linear motion components. So you have steppers, you have linear slides, bearings, belts, and stepper motors. Then you have all of the electronics, the wiring harnesses that go to the steppers from the controllers. You have the controllers themselves, all of the motor controllers that can blow up. You have the motherboard, which is basically a fancy Arduino, which is not really meant for production products, in my opinion. And then you also have a hot end, sort of an evolved hot glue gun, which you're pushing filament through at like 80 millimeters. 80 millimeters a minute, and at really hot temperatures. So PLA prints at 230 degrees Celsius, and this temperature control is done through a PID loop on the Arduino that could have been engineered by someone who hasn't studied like systems control or anything like that. So subject to temperature fluctuations, and basically at the end of the day, you get a machine that is relying on like luck to work properly, because you have so many things that are subject to failure that were designed not necessarily by engineers, and all have to work together, perfectly well to get a 3D printed part at the end of the day. And anytime you get like a new filament, or you're trying to do something that's pushing the limitations of the 3D printer, you're having to change settings, and one setting change, one small minutia of a change can vastly affect how the printer is operating as a whole, because as complex of a system as it is, it's hard to see what one change in one variable might make in the operation of the printer as a whole. And you're like halfway through the part and it fails, and you've wasted half a spool of PLA, or you forget to level the build platform. So there are all sorts of things that can go wrong. And what I often tell people as well is that in the Invention Studio, it's not necessarily always the printers that are at fault. It's kind of that they're in the Invention Studio. And I think most hackerspaces will tell you this as well. When you have an environment where you have a bunch of machines that are just open for anyone to walk in and use, we don't allow that with our CNC mills and water jets and things like that, because people can cut off their arms and die horrible deaths using those machines. 3D printers are kind of cute, and they're not going to kill you unless you're very, very creative with them. Which would be kind of hilarious to see. But anyways, we allow our 3D printers, we have them in a separate room that's open. Anytime we're open, we don't always staff that room, because we trust that any user can go in and Google how to use 3D printers. We have an internal wiki that documents how to use all of our printers. And since we have university funding and have the money to replace printers like once every year, and we can roll 30 new 3D printers in, we sort of just subject them to the masses and hope they do well, which is probably not the best mentality to manage machinery by. However, with 3D printers, since they're relatively cheap, that allows us to devote man hours to other places in the lab, like the CNC water jet, to make sure people aren't cutting their arms off. Because that would be really bad. A 3D printer going down is not necessarily as big of an issue, but they do require a bit of experience and knowledge to think, okay, well, if I put this different filament in, if I put ABS filament in this printer that's meant for PLA, then it's going to clog up the nozzle, and then it takes 2 hours to unclog the nozzle by someone who has experience with a 3D printer, and can just cause a lot of aggravation. Especially like when Alan said, sometimes something fails, and if you aren't an experienced user, not everyone can walk up to a 3D printer and say, oh, well, the build platform wasn't level, or the temperature wasn't up high enough. So without the proper expertise, these things can be a real fuss to make work properly. Oh, I'm still on YouTube. So just a couple of cool examples. There has actually been, and I'm kind of happy about this, a sort of new form of glitch art that 3D printers have spawned. And there are a bunch of websites now that you can just Google, failed 3D prints, and people will post like, okay, this is what this part was supposed to be, and instead I got this tennis ball, or this part here, if you remember back to the opening slide where I had the Replicator 2 on fire, this was actually one of their sample parts that comes with the printer. You would think that the printer would be able to properly print it out, but this one has made a mess of itself.
It goes on the altar of the flying spaghetti monster.
Yeah, it would be fitting there. Same thing goes with this Replicator 1 on the right-hand side. I don't actually know what was printing on that one, but it made a huge mess. We also had the printer I have in the sort of commons room called Ewok. Had this error where the wires on the x-axis stepper motor were not properly strain relieved. So when that wiring harness started to short out, the stepper motor would skip steps, which would result in maybe 5 or 10 layers of your part being stacked on top of itself like it should have been, and then it would start skipping steps, and you would have, nice part and then diagonally printed the rest of the part sort of off to one side, which is kind of hilarious to see as well. And one thing that I can say for Replicator 2s out of personal experience is that they are incredibly consistent in their failures. So since we had 3 of them, we got to watch Ewok happen and see diagonal parts and all laugh in unison. And then when our other 2 printers, what were they called? They were named after furry Star Wars characters, not Chewbacca, but his race. Wookiee, yeah. So we had Wookiee and the little small guys that...
Jawa.
Yeah. So Wookiee and Jawa also had the same issues down the road when they came up to about the same print hours, which was kind of hilarious. And I think it says a little bit about their engineering prowess to say that, well, they had this failure that should have been easily prevented by using proper wires and proper strain relief techniques, but at least all of them failed at the same time, and we could repair them. The printer Ewok that I have in the other room, you can take a look at and see all of the different parts that we've had to cut wiring harnesses and make our own and build our own extruders and things like that. And it's been a pretty interesting practical engineering exercise for us to have to repair all of those things, because we're basically learning as we go like everybody else is. And so what I learned very quickly is that managing 30 3D printers is not as easy as it may sound. You think, oh, well, they're fancy hot glue guns. What could go wrong? It's fairly simple. You're putting plastic into a heated hole, and then molten plastic is coming out, and it just moves around and piles the molten plastic on top of itself, and then you're all good. So that's very difficult. And then you have to keep up with fleet capabilities. So for instance, you never know from semester to semester what all of the students are going to be working on. One semester you might have a lot of mechanical engineers who are content with, well, I just want to make a plate with some holes in it for a simple bracket. And then the next semester you might have a bunch of BMEs come in, biomedical engineers who want to make realistic models of neurons or something that has to be very high precision. And then educating your entire user base, who could just be random students walking in from day to day, on how to use 3D printers, and then living with having to sell your soul to 3D printer overlords for a life of servitude. And that's what we call being a 3D printer master. So you are voted in by the executive council that runs the Invention Studio, and then you become responsible for managing our 3D printers. And then for your lifetime of duty, which is usually about a year in terms of how long you're responsible for them, all you get is crap from everyone else, because why aren't the 3D printers running all the time? Which is just an unrealistic expectation in and of itself. So these are all things that I would imagine anyone who has a 3D printer will experience on a day-to-day basis. Now on to the positive section of the talk. I will point to CoinSeg for a lot of really, really great examples of how 3D printers can be used for doing awesome stuff. CoinSeg is a Swedish supercar manufacturer, and they sort of make the best of the best cars, and they will only make about 6 to 10 of any particular model, which means that they're doing very limited production runs, which means that 3D printing becomes a viable solution for manufacturing really interesting, crazy parts. Like, for instance, this turbocharger has variable vanes on the inside of its housing, and is printed using an SLS, selective laser sintering machine, out of titanium oxide powder. So this is sort of like the state-of-the-art in metal 3D printing, and they've done several parts on their latest car, which is called the 1-to-1 out of titanium oxide. There's actually a 3D printer company in Sweden that does all of this for them. The turbocharger housings, as well as all of the exhaust manifold, they print their entire exhaust manifold from the headers to the muffler and catalytic converter and everything in one go on 3D printers, and since they're only doing 6 of them at one time, it's pretty feasible to actually do that. But I always try to give examples to people. Doing a full run of Raspberry Pi cases on a 3D printer is not really viable, because you could do the same thing on an injection molder, CNC mill a mold out of aluminum or steel, and then just churn parts out all day long on an injection molder and never have any reliability issues. Whereas trying to do thousands and thousands of parts day in and day out on a 3D printer is just not going to work very well, from what we've found with experience. Again, like I mentioned earlier, bespoke parts like cute bracelets or things like that. People have made like wearable planters for small plants that you can wear around your neck, or jewelry and things like that. 3D printers are cool with that, and short production runs are also good. As far as what we've done around the studio, this was a remnant of the DragonCon talk, because it was basically a bunch of people from the Invention Studio and some of our friends from MIT in a big room, and we all knew Kara, who was one of my good friends, and that was kind of funny at the time. So this is a Daft Punk helmet that I 3D printed, and one of my favorite uses of 3D printers is actually for prop making, because I'm too lazy to make a lot of the more detailed parts by hand. There are a lot of really awesome prop makers around Atlanta that will do this stuff out of foam, and then fiberglass and Bondo, and then sand for weeks, and then paint for months, and then have a really, really nice looking part. I found that I could 3D print something in about a week and then be done in another couple of days by just covering it in Plastidip, which is what I did on the Halo helmet. Also an arc reactor from Iron Man, which is pretty neat. So we've also used 3D printers for engineering projects. This example on the left is actually a whale tag that a friend and I made for NOAA. So basically in the black box are a bunch of potted electronics with barometers and IMUs and a little Atmel chip to log data. And so basically what they needed is an assembly that they could stick on the back of a whale and then release itself after 2 weeks, because on certain marine species, particularly mammalian species, you can't leave electronics or tags on them for more than a certain span of time. For these particular whales, it was 2 weeks, so they needed a reliable mechanism for releasing the tag off of the whale in a hydrodynamic casing. So we used 3D printers to make the valves, and this is the prototype, so they were all designed to be injection molded later on. The valve here in this case is a big cylinder with a stopper on the inside and a stepper motor that is servo that is waterproof on the back end. And then our hydrodynamic case was designed to be vacuum formed, which is another really neat thing that you can do with 3D printing, is make vacuum forming molds. And so this was the hydrodynamic casing, and we haven't tested it out yet, but it's going to Iceland in July, and we'll see how it does when it's put on the back of a whale. This is also a pretty cool example of a gear set that was actually all 3D printed in one go. So 3D printers can make things that are actually nested inside of each other. So the outside is actually turning. That's the reduced gear that is basically connected by a bunch of gears on the inside to the drill that's turning the whole thing. Would I actually want to use this on anything that I needed high reliability on? Absolutely not. He burned his hand, keeping it on the outside of the print while it's turning. Also, as you'll note from the video that I showed earlier, making battle bots is fairly common around the Invention Studio, and we've actually found that we can 3D print the entire internals of the battle bot and then just screw hardened tool steel to the outside. And some of the thermoplastics that we print with like for instance ABS, is very high impact resistant. So this entire frame was printed out of ABS, and the wheels were printed separately, but the entire frame was printed in one go. And then all you have to do is, all the holes on the outside are made to be, you can put threaded inserts in them. So you take soldering iron, put a threaded insert on it, and then you melt the threaded insert into the 3D printed part. And then you can screw hardened steel onto the outside, and it's pretty resilient, which is really neat. It saves you a lot of time in manufacturing, because normally if you're going to do this on a CNC mill, it would take a couple of weeks to design the part in CAD and then do all the CAM work and then do all the setup on the machine and buy all of your tools. 3D printing ends up being a cheaper, quicker option. And of course, we've also done some neat figurines. Someone made a chess set. These are a couple of the chess figurines. The clear print is actually an example of a print from our Form Labs machine. It was a SLA machine, stereolithography, that's done out of photopolymer resin. These guys, you can kind of see the layers of the prints themselves. So the little layers along the height of the part are where the separation of how it's been printed, and then we'll bring it down and then print more. So that's an example of areas where are prone to separation is between those layers. And that's also something to note in the surface quality of 3D prints are not always perfectly smooth after they've been printed. So you have to take that into account if you're making like a prop or something that you want to be perfectly smooth. It's not going to come out of the printer like that. You have to do a lot of finishing to get to that quality. We also have a paper 3D printer, which is fairly neat. And going back to like what I was saying about vacuum forming earlier, I've had a couple of experiments with doing vacuum forming with 3D printing. So you make a mold that's made out of PLA. Then you take that mold, you put it into a vacuum forming machine, which basically means you take a sheet of plastic, put it in an oven, heat it up to about 230 degrees Celsius. You drape it over your part, and then you have a vacuum pump on the bottom that creates a seal between the plate and the plastic that you've just draped over everything, and it will suck the plastic over your mold. And then you have a plastic piece that you can replicate fairly easily. You just put a mold in, and then you can have a piece in like 5 or 10 minutes, which is really neat. For instance, I'm making visors for my Halo helmet using this method. With PLA though, PLA melts around 210 degrees Celsius. So when you're draping something over it that's 230 degrees Celsius, you have lots of melting of your mold, which comes out to a part that's no good. It's warped in all sorts of weird ways. However, our paper 3D printer, which has a standard inkjet printer in the bottom of its casing, you take a file, like an STL file like you normally would with other 3D printers. It breaks it up into all the layers you need, prints out the colored patterns. This is something unique to the paper 3D printer as well. It can print in full color. So it will print the outlines of the objects on the sheet, and then you load the pile of sheets into the side of the paper 3D printer, which then takes them, picks them up, places them on the build platform, has a razor that goes around and cuts along the edges, and then it glues on the next sheet of paper, and you get a paper part, which is more resistant to thermal damages than like PLA would be. So for instance, you can paper 3D print a vacuum forming mold and then put it into the 230 degrees Celsius plastic and not have to worry about it melting like PLA or ABS would.
Is that 3D, is that connecting rod, is that FIA?
Finite element analysis, FEA?
Yeah.
Yes. So that's another neat
awesome.
thing. Yeah, you could take this into a meeting and say, okay, so I did FEA in SolidWorks, which is basically like the stresses going through the part in certain conditions, experimental conditions. You can go in and say, okay, our stress concentrations around the bottom of the connecting rod that would normally be connected to the drive shaft are a little higher than we want them to be. And since this is cheap, it's being printed out of paper, you get to do this for much less money than you would with plastic. And having to swap out plastic every time you wanted a different color would just be crazy. Yeah, go for it.
Have you ever 3D printed a working motor?
No, so that would be interesting. I have seen people who have printed like pneumatic motors, and also people who have made pumps that were 3D printed. But as far as doing the motor, I would have to, you'd have to be able to get the copper windings in somehow. So I guess you could print like the, and also you're going to have, you know, a ferrite core or ferrite stator or something like that. So I guess you could print like the housing using plastic or something like that. Or maybe using metal printers. That would actually be an interesting project to try out. I have printed turbines, so basically like the first half of a turbo pump, or not a turbo pump, a turbocharger, the impeller section that sucks air in and spits it out in a high volume. We were looking at trying to make a pump for a rocket motor that could do a high volume of liquid in a very, very small amount of time. So we were essentially designing this thing to be strapped to a three-phase brushless DC motor from like an RC airplane that can spin at a couple of thousand RPM and spin that impeller up and suck kerosene through and feed it into the rocket motor. Normally, turbo pumps and rocket engines will use like a steam reaction, and the steam will drive the turbine, but we thought we might be able to get an RC-grade three-phase brushless motor to do the same thing. However, spinning a turbine wheel up to a couple thousand RPM that has been 3D printed on a replicator 2 is not a very good idea. And you definitely don't want to be close to it when it blows up in your face. Fortunately, we had enough sense to like put it behind some acrylic, and we were all protected from it when it came apart. So any more questions? I think I actually ended up finishing on time, which was good. Awesome. Well, thank you all for coming out. I'll be around all night. Yeah, go for it.
What 3D printer would you recommend for like most stability or long lasting?
Yeah, so I definitely would say the consensus around our community of friends. So I was trained by a couple of guys who are now studying FDM technologies for a grad degree at MIT, and they have several other friends. We all sort of got together for this presentation at DragonCon and thought, okay, we want to give people our decision on what we think the best 3D printer is in the consumer market, and the Up Minis are our decision. You can buy these on Amazon right now for about $600 a pop. If you buy 4 of them at one time, they'll actually sell you all 4 for $2,000, which is a substantial savings, which is what we did with these. They print ABS, they have the heated build volume, they look really nice, and pretty much if a print gets through its first layer, you know the entire thing is going to finish. The Replicator 2s are sort of notorious in my experience for getting 90% through a part and then quitting out on you, which I would much rather sit in front of a printer and then have the part fail on the first layer like 3 times because the build platform isn't perfectly leveled or something like that, than I would get 90% through a part and then have the extruder clog and waste all of that plastic and all of that time.
So what is it about the Up Mini that makes it different, other than the fact that it doesn't have a full, that the replicator bots don't have a full casing, that makes the Up Mini better?
Yeah, so also on the inside of this, all of the frame and motion components are made out of metal, like nice high precision linear movement components. The MakerBot was sort of taken and said, how can we produce this in the cheapest and most marketable way? And they made some sacrifices for making it look pretty and making it really cheap, which is still like 3 times more expensive than one of these machines. However, the internal structure for all of the motion components, they're all very soundly mounted to metal pieces. So you have very few like flexing and warping on the components on the inside, which is really handy. The software is very easy to use, but it still gives you a little more control than the MakerBot software does. The temperature regulation is much better in these machines than it is on the MakerBot. Yeah, the list really goes on for a long time.
What is the build on?
So this is a 4.5 inch by 4.5 inch by 5 inch build volume. And sometimes people will look at that and they say, well, that's incredibly small. How am I going to do anything useful with that? And I usually share with people that I like to design parts that are sort of modular, that can be fastened together after you 3D print them. So like, for instance, the Master Chief helmet was done in 28 different parts. And I learned very quickly if I wanted to do a large print on one of the Replicator 2s, if it failed 98% of the way through, you had to print the whole thing over again, versus if one small part fails, then you can just print the small part over and over again. The other neat thing that I can show you, I've got one of the Halo helmet pieces in my toolbox in the other room. I designed pin holes in the part that I can insert alignment pins. So steel rods that go in between the parts, which add a little more structural rigidity between them. So you can sort of design with some cleverness if you do modular parts to have alignment pins or support beams or something like that on the inside of your part, which sort of allow it to be a little better than if you were just making one huge 3D printed object. Go for it.
Is there a 3D scanner you'd recommend?
So I've actually found the Microsoft Kinect to be just about as good as anything else on the market. We have one of the MakerBot, what's it called, the digitizer, and it's just a load of rubbish. I tried to scan a Chick-fil-A cup with the digitizer, and it was just looked like some sort of blob. So the resolution is very, very poor with digitizers. We have a structured light scanner, which basically works by projecting a image of essentially like black and white lines or squares, and then takes a picture with a really high resolution camera and then measures the deflection of the image that it knows in software. It's the true image that it's projecting versus the warpings from the object being there. That works fairly well, but you have to reposition your object by hand every time, and if you get off by a few degrees in how you rotate it, sometimes the software isn't great at compensating for that. There is the SDK for developing with Kinect that Microsoft released for Windows platforms, so it kind of sucks if you're on Linux or Mac, but if you're on Windows, you can download their development platform and basically hold the scanner and just rotate it around an object, and then the software will construct a mesh, point cloud mesh that you can then convert into a 3D model. So if you've already got an Xbox Kinect laying around, download the software development kit for it, play around with it. It's pretty great. I scanned the back half of my car and actually imported that shape into SolidWorks, and then used that to design a custom spoiler that I then made with a CNC router that we have in the studio. But it's very good for like getting the quick dimensions of a shape. You can scan it and then not necessarily go straight from your scan to printing something, but with a little bit of post-processing and CAD software, you can have something that's really usable. Yeah, and if you have any more questions, I'll be in and out of that room and trying out the networking of the hill. Thanks everybody for coming.